All right, for Hess's law, let's start by writing down what you see on the screen. Go ahead and pause for a few minutes. Okay, so the overall change in enthalpy for a reaction is equal to the sum of the individual steps taken in the process. So if we have a reaction like carbon reacts with hydrogen to give us CH4, we may not be able to look up or experimentally find the change in enthalpy for that reaction. And there could be a number of different reasons that it's not possible. It might just be like a reaction that's too energetic and will give off so much energy that you won't be able to contain it in a calorimeter. So something like that. But lots of different reasons. But what Hess's law tells us is that if we can come up with, if we have delta H's for other reactions, and those reactions can be added up to give us the overall reaction that you see here in blue, then we can also add up the delta H's for those individual reactions to get the delta H for the overall reaction we're going for. In this case, the producing CH4. So if we're assuming that the reaction is difficult or impossible to actually measure the delta H for, but we have some information about some other processes that have some of the same stuff in them, then we can sort of add them up. Okay, so here's what I mean by that. If you look at this first reaction, carbon and oxygen gives carbon dioxide, right? Well, carbon dioxide and oxygen are not a part of this blue reaction up here, but carbon is. And so what we can do is we can say, all right, we know this much. We know that carbon would react with oxygen to give CO2, and that would give off negative 393.5 kilojoules per mole. And then we look at the next reaction, and it doesn't have carbon in it, and it doesn't have CH4 in it, but it has hydrogen in it, right? And so we can use this information, the fact that when hydrogen is a reactant in this reaction, it gives off this much energy. But in the overall reaction, there's 2 hydrogens, and in this reaction, there's only 1. So what we're going to do is we're going to double this reaction. And so I'm going to just say, down here, I'm going to put parentheses around here, and I'm going to say times 2, because right now I only have 1 mole of hydrogen, and in my overall reaction, I have 2. So I have to get them equal to each other. And then finally, this last reaction has CH4 in it. It has 1 mole of CH4 just like our overall reaction does, but it has it on the wrong side. So what we're going to be able to do then is, instead of multiplying this one by 2, we are going to flip it, meaning we're going to write the exact opposite reaction. Okay, and so let's go through this and show you what this looks like. So the first reaction I don't really have to do anything to, but I am going to draw an arrow down here and just kind of recopy it. All right, so we have carbon as a solid plus O2 gas yields CO2 gas and has a change in enthalpy of negative 393.5 kilojoules. And then for the next one, we said we were going to multiply it by 2. So I'm going to take everything in it and multiply it by 2. So 2H2 gas. And then I had a half mole of oxygen in the original equation. So that's going to become just O2, 1 mole of oxygen. And then if I also double my product, it's going to give me 2 waters. 2H2O liquid. And our delta H also has to be doubled, right? So negative 285.8 kilojoules has to be multiplied by 2. And that gives me negative 571.6. Very important that we remember to also, whatever we're doing to the substances, we have to also do to the energy as well. All right, and then this last equation, we have to flip it. So instead of carbon dioxide and water being my products, they're going to become my reactants. So I'm just basically writing the reverse reaction. So CO2 gas plus 2H2O liquid and that's going to give me CH4 gas plus O2 gas as a product, and my delta H also has to be flipped. So it was negative 890.8, so now it's going to be positive 890.8 kilojoules. And so now that I've done everything that I said I was going to do, I'm going to add these up, right? And when we add these up, anything that shows up on the reactant side and the product side. So for example, if we have some CO2 on the left and some CO2 on the right, what that means is the CO2 is being produced by this step, but it's being used by this step. So therefore there's no overall or net change in CO2. So therefore we get to cancel our CO2 as long as the number of moles of both are the same. And then let's see, we also have, oops, and you know what, I forgot to do something here. There was a 2 up here, 2O2, so I forgot to carry that down when I flipped my equation. And that's important because right now, in terms of canceling, I have 2O2 on the right, and I have 2 separate moles of O2 on the left. But even though they're separate, they would still cancel with the 2O2 I have on the right. And I have 2 H2O liquid on the left and 2 H2O liquid on the right. So it looks like what I have left on the left, the reactant side, is a mole of carbon and 2 moles of hydrogen. And on the right, on the product side, I have a mole of CH4. And if I look at my overall balanced equation, that matches, right? So I'm going to go ahead and carry the stuff down. Carbon solid plus 2H2 gas yields CH4 gas. And then my delta H's, I just add them up. So I have negative 393.5 plus negative 571.6 plus a positive 890.8. So see what that gets you. Okay, and it looks like that gives me a negative 74.3 kilojoules. So I was able to use 3 reactions as sort of steps in my overall reaction and add up their delta H's to get the one that I was looking for. So let's try one more. So it says determine the heat of the reaction for the reaction shown. So this one here in orange. If we have all of this information, okay. Now I want to give you one hint, and I'm going to let you try this on your own. You can see what the answer should add up to, negative 906.3 when you're all done. But one hint here is you've got some your NH3, which is I'm sorry, I should have said O2. It's not the NH3, it's the O2. The O2 shows up in 2 different equations. So when you're trying to get your 5O2 for the left for the overall equation, and you're thinking, well, you know, I've got O2 in the first equation and the third equation, so which one of those, you know, like what do I do? Whenever that happens, you want to save that, sort of like set that substance aside and just focus on getting everything else correct, and the O2 should work out on its own, just sort of naturally. So try this problem on your own, flip or, you know, multiply the different equations, and then cancel the stuff that shows up on the reactant side and the product side. And we'll talk about if you had any difficulty getting that negative 906.3, we'll talk about that in class next time.